We're looking at the appendicular skeleton of vertebrates. So to start, we're going to look at the finfold theory, which is the theory that tells us how paired fins arose. And what we want to look at is a very primitive looking fish-like organism that does not yet have the paired fins, has this caudal fin right here in the back, but no paired fins yet. What we notice in these early primitive fish is that they have a fold of skin known as the ventrolateral fold, and within this ventrolateral fold, it is assumed that the fins developed and grew more robust. So ventrolateral folds in the body were stiffened by a series of endoskeletal pterygiophores. Pterygiophores just means bones, which is going to make the structure stronger and more well anchored. And so you can see here that within that ventrolateral fold, over evolutionary time, you end up getting these paired fins. You see the pectoral fin and the pelvic fin arising within that fold. Now, these pterygiophores are bony elements within those pectoral fins, and they get larger and stronger over evolutionary time. The series of these pterygiophores that's closer to the body are known as the basals, and the ones that are more distal are known as the radials. So basals are proximal and radials are distal. Additionally, what we need to do is we need to anchor these bones very strongly to the trunk of the fish. And the term that we use for these fusions of bones to the trunk are known as girdles. And so you would end up having a pectoral girdle and a pelvic girdle. Now, we have looked into what DNA and genetics could orchestrate this and what is in common among all vertebrates. And what we found is that these fins and eventually limbs, when we get to terrestrial vertebrates, are coming out of the ventral compartment. And so we have this ventral compartment that is obviously the place where these fins arise and also where these limbs arise. Now, to prove this to yourself, bring your hands to the front of your body and bring them together and touch them together and see how easy that is compared to touching your hands behind your back, which is much more difficult. The reason being is that they are extending out of the ventral compartment. Now, the gene that orchestrates this budding of the ventral compartment is known as engrailed 1. So engrailed 1 gives us the limbs coming out of the ventral compartment. The next gene that we're going to look at is known as the T-box gene. The T-box gene basically differentiates the anterior limb or fin versus the posterior one. So the T-box gene has these two variations. One is the TBX5, which gives us the anterior limb or the pectoral fin, and the TBX4 gives us the posterior limb or the pelvic fin. So this gives us the identity of each pair of appendages. In fish, the pectoral fins and the pelvic fins are morphologically different. And of course, in terrestrial vertebrates, like humans, for example, the arms and the legs are clearly morphologically different. The last gene that we're going to look at is known as the Sonic the Hedgehog gene, which basically promotes the outgrowth of the limb away from the body, meaning that we need to extend this bud outwards away from the body. We also need to give it an axis. So this proximal to distal axis, if you think about it, the limb is changing, it's differentiating from the shoulder to the elbow, from the elbow to the wrist, from the wrist to the fingers, and that's what the Sonic the Hedgehog gene helps with. It also differentiates through that axis the ventral side of the limb versus the dorsal side of the limb. You think about your thumb side versus your pinky side, and how those two are clearly morphologically different. Now, before we get to fish that are still around today, we're going to look at an extinct fish, a placoderm of the Silurian, because these were the vertebrates of their time, and they were the most successful vertebrates of their time, and we need to see how their fins were compared to modern day ones. So pectoral and pelvic girdles were present. You can see a much more powerful pectoral fin versus the pelvic fin. This is a general rule that in these fish, what we see is a much more firm pectoral girdle, a less firm pelvic girdle. That does change in terrestrial vertebrates, where the pelvic girdle becomes more stout and well anchored to the body. What we notice here with these fish, which we don't have in fish that are around today, is of course these plates of bony armor that they're famous for. That's why they're called placoderms. But that these plates of bony armor also extend into the fin. And so what you see are these plates, and you can see it really well in these pictures right here, which are these models, these three-dimensional models that show a very well-defined border right here of armor on the fin itself. And so this is clearly a difference between the ancient fish versus modern fish that we have today, which do not depict this type of armor on the fin itself. We are going to look at elasmobranchs next. These are the cartilaginous fish, which includes the sharks, rays, and skates. And these are, of course, around today. And the big thing here to note is that over here in this picture, you have the basal pterygophore. And then after the basal pterygophore, you've got the radials that project out from it. And that's, of course, why they call them radials. So remember that pterygiophores are the bony elements of the fin, right? And they're the sturdy bony elements of the fin. So the other thing to notice here is that after the radials, you end up having what we call fin rays. And so fin rays, there's a big distinction between the fin rays of a shark and the fin rays of the bony fish. So remember that the shark is a cartilaginous fish. That's where we put it in terms of classification. So the fin ray of the cartilaginous fish is going to be made of very thin ceratotrichia. Now, ceratotrichia means keratinized. So these keratinized rods are making up the fin rays. Now, it's hard to see in this picture from the textbook, but this real picture down here shows you much better what we're talking about. So here is the basal pterygiophore. Here are the radial pterygiophores radiating out. And here are the ceratotrichia, which are so thin that you can't even tell them individually apart in this picture. Now, in lab, we did dissect a shark, and that's where we can really observe these keratinized, very thin rods coming out of this cartilaginous fish. The other thing that sharks have in their pectoral girdle is this U-shaped coracoid bar right here. And what is distinctive about this is that the two girdles are attached and fused at the midline. Now, this happened over evolutionary time, and modern sharks have held on to this morphological structure. We will see that bony fish do not have this. So please make a note that this coracoid bar, this U-shaped bar, is a characteristic of sharks. Now we can see it here in this next slide. Here we have a primitive shark, and here we have a modern shark. You can see the similarities, but what we need to do, and it's hard to see in this picture, what we need to do is we need to get that U shape, right? Because from the ventrolateral fold, they were separated. What happens is that these two pectoral fins do converge onto each other and end up making a connection in the middle right there. And this is what we're looking at over time, is that we have this origin of the girdle. You've got this over time moving this way, this picture. And what you see is that these bones, they get more robust with the basals there getting thicker on both sides. And then the basals will eventually meet in the middle or in the midline of the fish to give rise to then a coracoid bar that's fused together, making a very, very powerful, strong pectoral girdle attachment. And in general, as we said, fish in general have a much more robust pectoral girdle compared to the pelvic. Just observe right here how more delicate and small and less powerful that pelvic fin looks in comparison to the pectoral fin. So here what we're going to look at is the pectoral fin and the pelvic fin of sharks, and how the pectoral fin is different from the pelvic fin, but also on the pelvic fin how the male and the female have differences. And so let's look at the pectoral fin first. So here is that coracoid bar. It's been cut right here in the picture, so you do have to imagine it will make that U shape with the other side. And you have the basals that are made up of right here, the protopterygium. And then after that, you've got the mesopterygium. And then the metapterygium, which is the one that extends the most out there and seems to be the anchor for all of this. The radials are right here further down, radiating out from the basals. So all of those are radials. And then here, notice how thin these ceratotrichia look like. It looks like hair. And in fact, the word trichia does mean hair. The word cerato means keratinized. So keratinized hair, basically. Let's look at the pelvic fin. So in the pelvic fin, you've got that iliac process, which will give rise to the ilium over time through evolutionary time. And then you've got the basal composed of the protopterygium and the metapterygium right there, which you can see that it is the one that extends the furthest down. After that, you've got the radials that project outwards from the basals. And again, you're going to need to have the fin rays of ceratotrichia, very, very thin, keratinized rays that are projecting out from the radial pterygiophores. In the male, the big difference in the male is, of course, the clasper, which we saw in lab. And the clasper is an intromittent organ for the male. It's going to be on both sides, and both are viable, but basically the clasper will be the way that the male will be able to bring sperm into the female. So the clasper will be an intromittent organ, which will be able to go into the female cloaca, and that's how sperm is distributed to the female. Next, we're going to look at bony fish, and we're going to look at the fins of bony fish and compare them to the fins that we just looked at of cartilaginous fish. So first, let's look at what they have in common. We still have the basal pterygophores and the radial pterygophores radiating out from the basals, and we still have the fin rays that come out of the radials. However, the fin rays are much thicker than the fin rays that we saw in cartilaginous fish. The fin rays in bony fish are called lipidotrichia, and lipidotrichia are usually ossified or chondrified, and that makes them much more thick than a simply keratinized rod. And so here you can see that these lipidotrichia can be much thicker and can actually bifurcate at some point. And that's really obvious when you look at a picture like this, for example, of this fish right here. And you can see that these dorsal fins are much thicker than the ones that you would find on a shark. And that type of thickness of lipidotrichia, you also are going to see it in the pectoral fins and in the pelvic fins. So you'll see it in the fins that are not paired, as in the dorsal fins, the caudal fins, and the anal fins. You'll see that lipidotrichia there. You're also going to see it in the paired pelvic and pectoral fins. Now, they may be further stiffened by additional keratinized rods at the very tip, and those are known as the actinotrichia. So just keep that in mind. It's either going to be bony or chondrified for the most part, but some keratinization can take place at the very tip of it. Now, the other thing that is different in the bony fish versus the cartilaginous fish, so first of all, just to get some terms out of the way that are some review terms, teleost just means that these are the most evolutionary recent bony fish that we have. And these are the ones that have the air bladders that you don't find in cartilaginous fish, which gives them buoyancy. Now, the basic structure of the pectoral girdle is that in bony fish, the clathrum is the strongest bony element of the dermal shoulder girdle. So you can really see it in this picture. There's the clathrum, which is basically most of this very powerful girdle there, making up the center of it. And then from there, that you'll have the clavicle, which will be very small. The clavicle will meet the opposite clavicle at the midline, but it won't be that very tough U-shaped coracoid bar that you see in sharks. So it's not as well anchored at the midline there as it was in sharks. So then how are we going to anchor this pectoral girdle very strongly to the bony fish? Well, from the clathrum, we'll have the supraclathrum, which extends out to the post-temporal bone. And if it's called post-temporal, and you can see it really well in this picture, that means that it has to be right behind the temporal bone. And the temporal bone is, of course, a cranial bone. So what we do is, for the bony fish, to anchor this down, we anchor it to the cranium of the bony fish, which is a big distinction between how this girdle is anchored to the body of the bony fish versus how the cartilaginous fish gains its robustness from that U-shaped coracoid bar. This slide is divided in half, and the top half, we're going to start by asking ourselves what kind of challenges a fish in water has to deal with from currents in the water. So, in general, the body of a fish is susceptible to deflections from its line of travel about its center of mass. Okay, so basically, think about yourself in water and having currents pushing you around. You have to be able to control your body within that water. And so that is one of the primary functions of fins, is to control for these movements in order to stabilize the fish. So let's see what these movements are called. The yaw is the swinging from side to side. So imagine yourself as this shark and you're moving forward and then you get swung from side to side. That's what this arrow is trying to depict, a side to side movement of the body of the shark. The next movement is the roll. So you imagine the line going through the center of the body, and the roll would be the spinning around that central axis. So that would be the rocking about its long axis. The pitch is the bucking forward and backwards, and that's depicted by this arrow right here. Right? So you imagine the nose of the shark moving downwards, the tail moving upward simultaneously. That would be an example of pitch. So clearly, all the fins have to be used for these to control for these movements. And of course, the pectoral and the pelvic fins are the ones that we're going to try to track from here on out to give rise to limbs. So we want to ask ourselves, well, which type of fin gives rise to limbs? And that's what this bottom half of the slide is dealing with. So we are going to start looking at lobe-finned fish. These are the fish, the sarcopterygial fish, that have a lot of musculature and very thick pterygiophores in their fins. And the first type of arrangement that we have in the fin is known as the archipterygial fin. And it's called archipterygial in the sense of archetype because initially we believed, because of a lot of extant or living fish that are still around today that are lobe finned, they have this type of fin. So we believed that this type of fin was the one that gave rise to the terrestrial limbs. Now the stem runs down the middle of the fin, and you can see it here with these basals going right down the middle, down the axis of that fin. The radials project outward, and that's these right here. So you can see the radials projecting outwards from the basals, and it looks very, very symmetrical. And that's known as the archipterygial fin. Now, with the fossil record giving us a lot more insight in recent decades, what we found is instead that there was a divergence in these lobe-finned fish where we see another type of fin called the metapterygial fin. And in the metapterygial fin, the stem of the basals is located posteriorly. And you can see it shaded here. These are the basals that seem to go posteriorly. So they're not going down the center of the fin, they're off axis, and then the radials project out from there. So it's a slightly different arrangement. Still very, very tough looking pterygophores. You're going to have a very, very fleshy musculature that goes along with that. So these are the ones that will eventually need to be tracked to then find out how we get to terrestrial vertebrates. Before we do so, let's look at the extant or still around living fish today. We've got the lungfish, and we've got the coelacanths. And just real quick to show why we had these archipterygial fins at first as the archetypes, or the ones that would have given rise to the terrestrial vertebrates. It is because the extant lobe-finned fish do have this arrangement. And you can really see it here in both these cases. You've got here these ball and socket type joints here of these basal pterygophores going down that central axis, and then the radials going out symmetrically on either side of that. Of course, these are bony fish, so you do have that clathrum right there, as you would expect, as that very central piece of the girdle. In the coelacanths, you also have this very similar arrangement with the basal pterygiophores going down that archipterygial axis. You have that clathrum being that most prominent girdle bone. And here is a cladogram showing us over evolutionary time how these girdles changed. So in these fleshy finned fish, you did have a split over here with the archipterygial pterygiophores giving rise to the modern lobe-finned fish that we have today. The cladogram continues this way, and you can see that meta-pterygial structure showing up with the basals being aligned posteriorly, the radials radiating out from that. And a very famous one is going to be Eusthenopteron, which we have a very good fossil of, and that is the link to Tiktaalik. And here you can really see basically that arrangement of Tiktaalik in that fin right there. As we move up the cladogram, there's Tiktaalik, almost the same in arrangement to Eusthenopteron. And after Tiktaalik, we end up getting our terrestrial amphibious organisms, which start to have these phalanges that are clearly now more for grasping and less for swimming as we move along evolutionary time. So real quick, here is Eusthenopteron, which is classified as a Ripidistan type of fish. And again, we have a very good fossil of this with both the pelvic girdle showing us the precursors to the pelvis, the femur, the fibula, and the tibia, and then eventually what will turn into the tarsals and the metatarsals after that. With the pelvic girdle, we still have that clathrum right there because, of course, this is a bony fish. And we do have the precursors to that humerus, that radius, and the ulna, giving rise to the carpals and the metacarpals after that. And eventually, over time, we can imagine how the phalanges would extend from there. Now, these early Ripidistan fish like Eusthenopteron their musculature, we believe, was probably too weak to supply propulsive thrust on land. So this image right here at the top A is showing us a ripidiscian in water being able to use that fleshy fin for undulations in the water and thrust, lift and thrust. That musculature would be adequate within an aqueous environment. However, if we imagine that Eusthenopteron being on land, we believe that the musculature was too slight or not strong enough to support the body weight of that fish. So most likely, these fins right here, and this B right here is on land, these fins would be more like pegs or pivot points where the fish could put some pressure on that fin and use some sort of rotation and pivot on land. So some movement was possible, but definitely not enough to completely be fully mobile on the land. The next big leap in the fossil record after Eusthenopteron is Tiktaalik. So with Tiktaalik, what we see is the loss of the pectoral girdle attachment to the skull. And so you can really see that here, where the pectoral girdle seems to be independent of the skull. So you have this very clear divide there. And what that does is it narrows the trunk at that location. And what we see is therefore the development of a neck, which is a terrestrial adaptation to move the head around on land. Because after all, if you're on land, your limbs are anchored down to the ground or to the substrate. So when you need to turn to look and to scan your surroundings, if you're anchored down with your limbs on the ground, you need to have a neck to be able to move your head around. So that's clearly a terrestrial adaptation. And so in this picture, what's nice about this is that you see that you have the water and the land here, where basically it's clear that Tiktaalik was amphibious, could definitely swim because this limb looks very much like Eusthenopteron, so that it was clearly swimming, but also probably very muscular, probably could do push-ups, could probably start to walk on land pretty easily, which Eusthenopteron probably could not, and started to develop a neck, which allowed for it to move its head about. So we are looking at a timeline here of how this goes in the fossil record. We are quite lucky to have Eusthenopteron, a very good fossil of Eusthenopteron dated at 385 million years ago. Clearly a fish, and probably using its fins as pivots on land, but not being able to actually hold its own body weight. 375 million years ago, a fossil that's dated to 375 million years ago, we have Tiktaalik, a very good fossil of Tiktaalik, where we see a neck and a more robust girdle, showing us that probably Tiktaalik was amphibious, but could in fact walk on land and hold its own body weight. Further down, 365 million years ago, we see several different similar animals, but one is Ichthyostega, showing a lot more robustness of the limbs projecting outwards more, and from what we can tell, could pretty easily stay on land. The other thing that we notice is that the phalanges are starting to form there, showing us that this limb is now adapting to walking rather than swimming. And so here is Ichthyostega. Um, what we notice here is a very, very robust girdle. Both the pelvic girdle and the pectoral girdle are very robust. So what we see is that the pelvic girdle was composed of a single bone with three parts: the pubis, the ischium, and the ilium, which is, of course, what we see in modern day terrestrial vertebrates. And very importantly, the pelvic girdle became attached to the vertebral column. And so what we see is a kind of switching of robustness where the pelvic girdle starts to get more robust and more attached and anchored to the vertebral column compared to the pectoral girdle. So in general, we see this switching of robustness and anchoring of these girdles as we move away from water and on to land. We still have in the pectoral girdle that clathrum, because of course we have this connection to the past of that bony structure with the clathrum. But notice that pectoral girdle is clearly much further away from that cranium and is now independent of that cranium, giving rise to a neck. This organism clearly could move its head around, clearly was very comfortable on land, was probably also very good in water. You see that the humerus is becoming more is robust. You see that radius and ulna are going in parallel, a much more classic shape of bones as what we would expect, and phalanges projecting outwards. On the pelvic girdle, you've got the femur articulating with the pelvis, and you've got the tibia and the fibula in parallel, followed by tarsals and metatarsals and phalanges coming out of the lower limb. The next slide is to give you an appreciation of the fact that there were a multitude of different organisms that had similar body types, so that we should not think of evolutionary time going too sequentially here with one organism simply giving rise to the next. So we do have an array of these. We can only spend time on some of them. So this is more of just a survey for you to realize this. We're only going to pick a few here. So Eogerinus here looks like a swamp creature, a very big body type. Based on how large this body type was in comparison to its limbs and how well those limbs could hold up that body weight, it has been thought that maybe this Eogerinus was maybe some sort of swamp-like creature who lived in shallow waters, could probably go on land, and but was also very comfortable in water and was probably a very powerful swimmer. But you can nevertheless see that this basic limb structure is now there and is now going to be in all of these vertebrates from here on out. Look at how large Eogerinus was, pretty terrifying right there compared to the human. Just some others in this survey. We can't look at all of them, but just a few more just to give us some appreciation that at this time there were a lot of different types. So Ariops right here. This one right here, a pretty stout looking organism. Look at how compared to Eogerinus, clearly there was a lot more distance between the abdomen and the ground. So probably this one was much more terrestrial than Eogerinus. And look at how stout these girdles were. That is a lot of bone mass. And every time you have a lot of bone mass, you have very powerful musculature that goes along with it. So still probably amphibious, still probably very good in water and on land, but clearly colonizing and being comfortable on land. And then Cacops right here, small but robust. Looks like a like a mini tank right here. So compared to the human, you notice how small this was, but look at that shoulder girdle, look at that pelvic girdle, look at these this radius and ulnar parallel being quite long and projecting out, and the fibula and the tibia right there. A lot of space between the abdomen and the ground, so very comfortable on land. Here we want to ask ourselves, how many digits was the original number of digits? And when we look at modern day terrestrial vertebrates, we see that 5 is the magic number, and that if 5 is the magic number, we typically see in the fossil records that you either add to the number 5 or you take away from the number 5. So the question is, was the original number 5, was pentadactylus, or 5 digits, the original? Well, from what we've got, when we look at the hind libs of Ichthyostega, which had 7 digits, and the manus, or the forelimbs of Acanthostega, having 8 digits, we see that the number 5 was probably not the original magic number. And so what we do think is that, in fact, these late Devonian animals were more polydactylous, that they had more than 5 digits, and the number 5 digit pattern is a later stabilization. So we do use the Latin terms manus for the upper limb hand area, and we use this because, of course, humans being human-centric, their hands and their feet have very different functions for each other, but for a lot of quadrupeds, the functions of the upper limb most distal end and the lower limb most distal end is quite similar. So we use Latin terms in order to not make it so human-centric. So manus, and for the lower limb, most distal part of the limb, we use the term pes. So here is the Ichthyostega hind limb and the Acanthostega forelimb, and you can see right here that we have 1, 2, 3, 4, 5, 6, 7 on the Ichthyostega, and 1, 2, 3, 4, 5, 6, 7, 8 on the Acanthostega. And again, the term that we use for that is polydactylus. And then on the right side, what we see is that over here, what we see is that the pentadactylus structure did become the standard later, and so this is kind of a generic view of what the basic terrestrial hind limb and forelimb would be like, where you have on the hind limb, you've got the tibia, the fibula, you've got a set of tarsals followed by metatarsals, and then phalanges numbered 1, 2, 3, 4, and 5. Hallux, meaning the thumb side or the big toe side, is number 1. For the forelimb, you've got the humerus, the radius, the ulna. After that is going to be a set of carpals, and then the metacarpals after that, and the metacarpals then will give rise to phalanges. Pollex for thumb, number 1, index 2, middle 3, ring 4, and pinky 5. Now, the formal term for a limb is a chiridium, and a chiridium just means it's a muscular appendage with well-defined joints bearing digits. And so that's really the big thing here. Now, just to remind us where we came from, is that when we looked at the fish, we had the fin that had these basal pterygophores and then radial pterygophores, and then after that we had the fin rays. And so that's where we started the conversation, but now we are in these terrestrial limbs, and now that we have these well-defined joints bearing digits, we are now calling them these chiridia. Now, chiridia of tetrapods have three clearly recognizable regions. And region one is known as the stylopodium. The stylopodium is the region that attaches to the girdle. Here is the girdle up here, and the stylopodium will articulate with the girdle right there. So with the upper limbs, what we've got is the forelimb part of the upper limb is known as the upper arm. And for the hind limbs, or for the lower limbs, we have that stylopodium is known as the thigh, right? But basically, it's a very similar morphological structure, whether it's the forelimb or the hind limb. Now, the second region that we have, or the middle region that we have in the chiridia, is known as the zygopodium. And the zygopodium is characteristically going to have two internal supportive elements, the ulna and the radius in the forelimb, and the tibia and the fibula in the hind limb. Now, the forelimb, we call it the forearm, and in the hind limb, we call it the shank. But in both cases, you would have these two long bones going in parallel. And again, it's either going to be radius and ulna if we're talking about the forearm, or tibia and fibula if we're talking about the shank. The last part, the third part, or the most distal end of the limb, is known as the autopodium. The autopodium is going to be given the Latin terms, the manus for the forelimb and the pes for the hind limb. And again, these are the Latin terms for hand is manus and pes is foot, but we give it the Latin term because, of course, humans having hand and feet don't want to be too human-centric when we refer to other terrestrial organisms, and so we give them the Latin term to try to be more general about these structures. But basically, if we're talking about a human, we have the hand for grasping and the foot for standing, but this does not apply to all tetrapods, of course, so we use the Latin version, manus and pes.